course on quantum computing. The first lecture was devoted to, in some sense, telling you the basic essentials about quantum computing. And for that matter, for anything, when we talk about essentials, you want to ask, what is that thing and why that thing, right? And that's what we studied. So can you not look at this part and tell me what is quantum computing? Right, because what is computation? Computation is trying to encode your computation in some kind of laws of physics. What is quantum computation? You want to encode your computation in quantum systems, right? So you will use quantum systems to compute. And why are you able to compute? Because quantum systems obey quantum mechanical laws. Correct? This is what I exhibited using different kind of laws like the billiards ball computer or the computing by the insect, right? So that idea is clear. Now we want to do it using quantum mechanical principles. Great. But then you can take any possible laws and start doing computation over that. Why quantum? Quantum is a theory of almost everything. And secondly, more importantly, why efficient? Why resource efficient? Why do we feel it is resource efficient? Because it is counterintuitive to classical laws. You have classical laws, you have quantum laws, they are very different. So if you start with different laws, probably you can compute things differently, right? That's the hope. And today's lecture again is going to be very, very light. It is focused on convincing you that quantum mechanics is actually weird. Okay, so it's going to be very light. Probably in between I will talk about randomized algorithms, but mostly I'm going to tell you experiments which prove or which show us that quantum mechanics is weird. And my hope is that after today's class you are convinced that this is something where we should definitely take a look. It is weird enough for you to say, I want to study it for next 3-4 months. Right? That's our objective. Look at quantum mechanics and convince ourselves that, oh my God, this does not look like classical computation. And then, side effect would be that what we see today will actually be used to create quantum algorithms. The first simple quantum algorithm actually I will in some sense derive from the kind of physics experiments we are going to see today. Okay, so yes, this is not very technical today, but I want you to pay attention of why I think this is surprising or why you should be thinking that this is a surprising phenomenon. You might have seen it in your physics experiments. I want to take a closer look at those things. Sounds good? Great. So let's start with something called Mach-Zehnder interferometer. How many people know what a Mach-Zehnder interferometer is? 1. Okay. 2. Okay. Great. And people who are from physics, I would say that take off your physics glasses and put on your computer science glasses. Because if your physics glasses are on, this will not seem weird. You have been taught enough to not feel that this is weird. Okay? Great. We are all classical people and let's see why we are in 1900s and why we should be surprised. Okay. So for this Mach-Zehnder interferometer, the first thing is what we call a beam splitter. Okay. These are going to be all physical objects, quantum physical objects, which will later be converted into some kind of operations on your quantum bits. Okay. So now this is a beam splitter, and as it says, its name, it is going to split the beam. What does it mean? If you shoot photons like this, you have a detector placed here, you have a detector placed here, you will see half the intensity going there and half the intensity going here. I should probably place it correctly. So, okay, so you can say that half of the time the beam passes through, half of the time it is reflected. Okay. So what do you expect? When you place the photons, it goes half the time here, it goes half the time here. Okay. And more importantly, we have the devices where you can shoot photons one by one. Okay. Even if you shoot photons one by one, half the photons will go here, half the photons are going here. Is that weird? Not really, right? This is like a coin toss. Correct? So, what is happening? Every time photon goes through this beam splitter, it tosses a coin. If it is head, it passes straight through. If it is tails, it goes up. Okay? So, we can model this going up and going down using probabilistic computation, right? Which is not quantum. We can do probabilistic computation. I can give this computer an ability to toss a coin, apply things randomly and calculate things randomly. That is not surprising. How many people know what randomized algorithms are or probabilistic computation is? Slightly higher, probably, so that I can see. Okay, so let me give you, so let's take a detour and at least have some idea about what probabilistic computation is, so that we are on the same page. So probabilistic computation, randomized algorithms, same thing for us. Randomized algorithms, again, we will stop, we take a detour, we finish randomized algorithms, we will come back to Mach-Zehnder interferometer. Yes?
Sir, is it so that we have first conducted the experiment and then we are software becoming unfocused randomly?
So exact order I can't say, but the future things, there were many of these were thought experiments, and later people actually did the experiments and showed that yes, this is indeed happening. That is a very good question. We will answer it as we go. So the question is this essentially randomness? Because if this is essentially randomness, then there is no point of making a quantum computer. What I am going to convince you is that this much seems like randomness, can be explained by randomness. I will make this device slightly more involved and suddenly you can't explain it using randomness. Very good. This is the exact question, right? So it looks like randomness right now. With half the probability I am going here, half the probability I am going there. I will make this experiment slightly more complicated and suddenly your probabilistic interpretation will vanish. You cannot explain it using randomization. And that's why I want to take a slight detour and tell what randomized algorithms is, right? So that's why, okay, so we will do this, don't worry, but first let's look at what is a randomized. What do we mean by this? So what kind of algorithms have you seen till now? Famous algorithms? Deterministic, but Dijkstra's. What else? Binary search, quicksort, things, right? So there, what is your input? Input is, in the case of quicksort, it's a list. In case of binary search, it's a list, but the input is fixed, right? And if my input is fixed, my output is fixed, correct? Now, yes, this is the ideal case. This is what I call deterministic computation instead of randomized. This is the usual computation you have studied. Most of, like all of you have studied till now. What happens is, you have an algorithm A, you give it X, you get an output AX, correct? And this AX only depends on X. I have an algorithm in mind, it depends on X. And then what do we want? AX is indeed the correct answer. It does what I want to do. If A is a sorting algorithm, then AX should be a sorted list of X. Correct? So my algorithm should work every time. Right? Unfortunately, this is too strict for most of the useful problems in the nature. Okay? So this is too strict in the sense that many problems we can't solve using a deterministic algorithm, or in most of the cases this is too expensive. This might take too much time. And obviously we don't have. We are greedy, lazy, all the human vices. So then we want to quickly finish our computation, but that means there has to be a trade-off. Okay? And one possible trade-off is accomplished using randomized algorithms. What do I do in randomized algorithm? I get an input X, but then I toss some coins, okay, which I will encode by randomness. Okay? So in the process of algorithm, my steps depend on my input, but it can also depend on coin toss. It could be as weird as, if I get a head in my coin toss, I will multiply the first 2 bits of my input. If I get tails, I will add them. So depending on what my random coin toss comes out, my procedure can differ. I can apply AND gate if my random bit is 1. If my toss is tail, then I can apply OR gate. All those possible cases are there, right? So in some sense, now my output depends on X and R. Yes. Okay. So this is one way to capture a randomized algorithm. It gets fixed if there is I fix the random string. Or other way to understand it is to say that now my AX is a random variable. Okay, and if you don't know what a random variable, you should definitely read and make sure that you understand the random variable. Right? So random variable means with some probability AX takes some value. It's not a fixed quantity. Correct? But now what does it mean that AX is actually a correct algorithm? It is doing what we want to do. Let's fix the case of sorting. X is a list. AX was the sorted list of X. What do you want AX comma R to be? Do you want it to be the sorted list of X? Ideally, yes. But there are so many choices of R. Do we want AXR to be the sorted list for all R's, or for some R's, or for at least one R? Do you see the question now? As you change the definition of your algorithm, your definition of correctness needs to be modified. How did you change the definition of the algorithm? You said that now I can choose a random string. Okay, so let's say I take 10 coin tosses. Then how many choices are there for the random string R? 2 to the power 10, right? So I have 2 to the power 10 R's. I am asking for a particular X. I have fixed algorithm, fix X. I say that this algorithm is correct, this randomized algorithm works if I could say that for all R's I should get the correct answer, for some R's, for most of the R's, for at least one R. You should get the correct answer. Which one should I choose? Okay, so let me write all R's, most R's, at least one R. What about all R's? Exactly. If my algorithm is working for all R's, then I will just pick one R and just run my algorithm on that R. Right? Why do I actually need to do a random coin toss? So this will not give us any extra capability. This will lead us back to deterministic computation. Right? So if I say that my algorithm has to be correct on all R's, then the power of this model will be exactly the same as deterministic computation. That means it is going to be extremely slow, limited, right? Whatever way you want to call it. So then this is not all. What about these? Let's have fun. Let's have a voting contest. How many people for most hours? How many people for at least 1 hour? See, that's why we have democracy. This is what we call, in some sense, non-deterministic computation. There is more to it. You have to be able to figure out which R that is. In someone can give you this R as an advice, and then you get it correctly. But the point is, if it is only true for 1 hour, then think of it in the use case. Which R should I use? I will be correct with very, very small probability, and that's not what I want. Then my algorithm is correct with 0.1 probability. Then do you want to use that output? No, it is much better if I am correct with probability 0.9. In most of the cases, I get the sorted list out. Okay, so then this is the definition. Okay, yes. 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 Good. So you are going to the correct direction, but that requires much more work. It depends on whether your algorithm is one-sided or two-sided, right? And then it depends on what do you mean by few. Because I have not quantified most, I will say a constant fraction is most. Okay. So if you want to go into details, then I can define most in a certain way, but the point is the probability should be significant of giving the correct answer. Yes, but the guarantee we can give is at most 1 hour, that at least 1 hour it is correct. See, again, in all these cases, we would know exactly for how many hours it is correct. We need to give a guarantee. So when you create a randomized algorithm, you should be able to say, pick your favorite input. My algorithm will work for at least 2/3 of the hours, or at least half of the hours, or at least 1/3 of the hours. So that guarantee you have to provide as an algorithm design. Okay? Yes. You will see the analysis techniques. We will go through this, but in the analysis techniques, you can say that if R is of this kind, then I get the correct answer. Again, there's a difference between knowing the answer and computing the answer. Knowing the answer does not require any time bound. Computing, you want to be efficient. So that's how it is different. In analysis, you can say, okay, this is my answer. And we will see examples, don't worry. Okay. So yeah, so randomized algorithm is, I say that my algorithm works for most R's where R is the random string. Notice, I am not taking the probability over X. This is true for all input. You can take your favorite input, my algorithm will work for most of the R's. Okay, it is not like my algorithm is working for most of the inputs. And other way in which I can relax this notion of correctness is, you will always compute correctly, but your expected time spent. So for some hour, you might take small time. For some hour, you might take more time in computation. Your expected time is small. Okay. So another way, another orthogonal way of correctness is let me revise it once more. When you create randomized algorithms, you say that you have some random choices. But since you have modified your algorithm, you want to give some notion of correctness or some notion of when these algorithms are useful. There are two notions. One is when we say that our algorithm works for most of the random strings. Okay. Other one, and in this case, what is your running time? The worst possible running time over all possible XNRs. Right? So your algorithm has to be correct on most of the R's, and the time spent I will count as the worst case time over all possible XNRs. In some sense, it should take less time on all X and all R's. But the other way I can make it say that, oh, this randomized algorithm is useful for me is, for every R I get the correct answer, but my time cost, the cost of algorithm is computed in the expected sense. In expectation, I will get the answer correctly. Sounds good? Okay. So these are different notions through which you can do a randomized algorithm, right? But again, the point remains, you toss a coin that allows you to kind of branch out and then have a relaxed notion of computation. And I think this all seems very fancy and not very useful if I don't give you an example. So let me give you an example. How will you compute the value of pi? Approximately, how can you approximate, how can you estimate the value of pi? Anyone has an algorithm? Sorry, why am I writing LaTeX? This is the problem with typing too much LaTeX. Yeah, how to estimate the value of pi? Any algorithms? Sorry? Converging polynomial expression or something.
Polygons, like bonding it with polygon.
So again, you are taking me a method, not an algorithm. How will your algorithm look like? Very good. You have some infinite series. It requires a lot of math, proving that this is correct, and then you know. Any very simple randomized algorithm? You have seen randomized algorithm? Yes. Yes, you go to a bar. For most of the problems in my course, you go to the bar, you can solve it. Right? What do I mean by that? This is your bullseye. You start throwing darts on this and count the number of darts which are inside the circle as compared to the total darts inside the square. I'm assuming you are not that bad that you will hit outside the square. Correct? What do I mean by that? What is the area of the square? 1. Correct? What is the area of the square? Pi? Seriously? Pi square? Oh my God. Pi square by 4. Because you are not going to write down on page and paper, all of you are giving me wrong answers. Once again, gets back to my famous statement. Undergrads at IIT Kanpur are great at giving very quick wrong answers. What is the area of this circle? What is the radius? Half. What is the area of the circle? Pi r square, pi square r. Again, note down on a pen and paper, try to do it instead of giving the first answer which comes to your mind. Math is done in a more hard-working way, right? So the area is pi by 4, this area is 1. That means if I count number of darts in circles divide by number of darts in square, this should be approximately pi by 4. And again, I gave you a physical process, I did not give you an algorithm, but algorithm is easy. You pick a number, two numbers x comma y between 0 and 1, and then you calculate x square plus y square, see if it lies inside the circle or not. If it comes at the circle, you count it as hitting the circle. Okay, then you can calculate this fraction. This should give you intuitively something close to pi by 4. You multiply it by 4, you get the estimate of pi. Right? This seems believable, but what is the guarantee? If you don't know this, probably read about Chernoff bound law of large numbers. So this is just telling you what will be utilized later. For now, I will just stop at this intuitive explanation. We will cover this in future courses. I will formally, mathematically show that yes, with high probability, we will get an estimate close to pi. But the tools I will require are these. If you don't know them, read about them. Or in general, read about concentration inequalities. Okay? And if you read about concentration inequalities, then as an exercise, you can try to prove that this algorithm works. That means with high probability, it will give you a good approximation of pi by 4. Okay? So now we have some idea of what probabilistic computation is and how it can be useful. Right? Sounds good? So now we want to make sure that quantum computation is not probabilistic computation. Because if quantum computation is like probabilistic computation, then we are wasting our time. We already know what randomized computation can do, cannot do, or we know much more. We don't need new devices. We can just perform these computations using our computers. Good? Questions? So let's get back to Mach-Zehnder. You are okay? Right? Again, you can read something about randomized algorithms, some books, probability, to make sure you have these concepts. Quantum mechanics, quantum computing is inherently probabilistic. Except in the beginning, we would like to compare our performance of quantum algorithms with randomized algorithms. Okay? So then we should have some idea of what randomized algorithms are. Otherwise, the beauty of quantum computing is at least lost. Get back? Yes, questions? Before.
So in this case, you have to like throw some answer and make an estimate.
Exactly.
There is another like physical situation where there is a block of 1 kg and there is a block of like 10 bulb and kg. And both of them collide. There is a wall. Both of them collide elastically, and number of elastic wedges are the limits of.
So I'm not saying this is the best randomized algorithm. This is the simplest randomized algorithm which everyone can believe easily. Yes. So yes, if you go into the detail, you have to actually answer in how many tries, how many darts should you throw so that it is, 0.1 close to pi or 0.2 close to pi. So the number of darts will depend on what approximation factor you want here and what probability of success you want. And is that the best thing? I'm not saying it is the best. It's a simple algorithm which everyone can get convinced about. You can do it in different. This is not the best algorithm to calculate, estimate the value of pi. This is not a course on randomized algorithms, right? So this is just to understand what randomized algorithms are. But thanks. Why don't you send a link of that algorithm in the forum so everyone can read about it and they will have fun with this. That would be nice. Okay. Thanks. Okay. Randomized algorithms done. Let's get back to what? Why are we reading Mach-Zehnder interferometer? Quantum mechanics is weird. Yes, good. So it is not weird up till now, right? Because this I can explain by probabilistic computation. I will just toss a coin, head, I see it on detector 1, tail. I see it on detector 2. Very, very simple explanation. Now, let's have slightly more fun. These are beam splitters. These are what we call mirrors. They will always reflect. Okay? So if a beam comes through, it can go like this, it can go like this. Sounds good? This is called Mach-Zehnder interferometer. It's not a lot more difficult. What I have done is, instead of placing one beam splitter, I have placed two. This mirror, don't get confused, it is just to make sure that light again goes back to the same beam splitter. Okay? So this mirror's role is just to make sure that the light is going back to the beam splitter. And then once more, the light can go up, can go straight. I can detect it using these two detectors. Correct? Now people who have not heard of Mach-Zehnder interferometer, tell me how many times or with what frequency or with what probability should I see the photons at detector 1, with what frequency I should see the photons at detector D2. Again, don't be an undergrad, don't shout out the answers, take your pen and paper, calculate. The question is clear? If there was just one beam splitter, I see it 50% times here, 50% times here. Now, I have two beam splitters. How many times do I see photons here? How many times do I see the photons here? Go ahead, calculate. Use your pen and paper. It is there for a reason. The reason is doing the calculations. It's very easy. You can do this calculation. And then you will vote. Again, 50% the photon goes here. 50% it goes here. You can send this on forum if it is very interesting news article. It's okay, it's okay. Right? So 50% time it goes here, 50% time it goes here. So this path I'm taking with 50% and then it splits up. This path I'm taking with 50% probability, it splits up. Computed? Everyone has some sort of answer, some sort of conviction. How many people for one? Option 1, anyone? One person. Option 2, are you physicist? 3. Right? Clearly, the probability is 50% here, then this goes as 25%, 25%. You can write half, 1 by 4, 1 by 4, whatever you like. 50%, 25%, 25% more. 50% here, 50% here. Sounds good? When you do this experiment physically, I have seen this happening in front of my eyes, you will never detect anything here. Or one of these detectors, depending on how these are placed, but you will not see any photon at one of the detectors. You will only see photon at one detector. Quantum mechanics is So I always forget which one do you see, physicist, D2? Do we see it at D1 or D2? Path lengths are equal, yes, obviously. I don't want to have spatial. Yeah. So, not just more photons, you see only photons at D2. Yes, yes, that's what you are going to discover. Okay, I'm not going to give you a reason. I'm a computer scientist. I will tell you how I can use it to make fun algorithms. But today's task is to make sure that I can't explain this phenomena using